Good morning. I will present you some recent work carried out in the group for Thermo-Fluid dynamics at TU Munich related to shape optimization. In this work, we propose to compute shape sensitivities from the adjoint fields, and that without using the Hadamard formalism. If you're not familiar with that one, this will be shortly explained in a few slides. Instead of Hadamard formalism, we propose a mesh perturbation method. We study thermoacoustic combustion instabilities, and in that context, shape optimization aims at modifying the shape of a burner and thus acting on the flow field, the acoustic field, and heat losses to dampen or suppress combustion instabilities. By instabilities, we mean the framework of linear stability analysis that assesses the evolution of infinitesimal fluctuation, for example the pressure, around a base or a mean state. If these small fluctuations are amplified, then the system is unstable. We need an evolution equation for these small fluctuations. A standard one for the pressure is the Helmholtz equation. That models the interaction of the acoustic cavity modes in the combustor with the flame dynamics using an external flame model and neglecting the presence of a flow. By looking for the solution under this form, we end up with an eigenvalue problem. And by solving it, we find the eigenvalues lambda that we can plot in the complex plane. If at least one of them has a positive real part, then the fluctuation is growing in time and the system is unstable. So the question is, can we perform a modification of the shape, here termed as delta omega, to shift the unstable eigenvalue by a delta lambda that will bring it to the stable half plane. This shape modification follows a vector deformation field V and has an amplitude of theta. And we define the shape derivative or the shape sensitivity as the limit of the ratio delta lambda by delta omega for vanishing amplification of the shape modification. We now want to find the deformation field such that the shape derivative points toward the stable half plane. A first strategy to compute this shape derivative is to choose a finite difference approach. The shape is slightly modified and the new eigenvalue is computed for each of these modified shapes. Then the shape derivative is computed by the difference between the original eigenvalue and the one for the modified shape. However, solving the eigenvalue problem is the expensive part of the process. So one would need to solve a large number of eigenvalue problems to get the optimal deformation field delta V. And this is overly expensive. Instead, we can get the sensitivities from the adjoint fields. The adjoint solution, here the purple P, is defined from the original eigenvalue problem through this scalar product. And it is also called the left eigenvector. It is the solution of this equation here with L, the original eigenvalue problem, for any vector P. This adjoint field can be combined with the Hadamard formalism to express the shape derivative under this expression. It requires much more analytical derivation than the finite difference approach. You can find this derivation in those papers, for example. But it is computationally highly efficient, and that's the strength of using a joint method. Because the expensive task, solving the eigenvalue problem for the eigenvectors and adjoint eigenvectors, is done only once. And the shape derivative for any deformation field V is computed by a simple boundary integral, which is super cheap compared to solving an eigenvalue problem. So you can test any shape deformation and compute the resulting shape derivative for a large number of deformation field V of different shape modification by doing this simple cheap computation. This is the state of the art for the Helmholtz equation, but there's a but when using this equation, which is that the Helmholtz equation is a hybrid approach in which the flame dynamics is modeled via an external flame model, an ad hoc flame model, for example a flame transfer function, in which the flame is frozen. This means that the shape modifications will not be reflective in the shape sensitivity, only the modification on the acoustic field. In that sense, the resulting shape derivative is incomplete. And this is a major showstopper for shape optimization based on Helmholtz equation, because it cannot be used to optimize the shape of injectors, for example. In practice, it is limited to optimizing the shape of the plenum, so far upstream from the flame. Instead, we propose to use a monolithic approach by opposition to hybrid that does not neglect the base flow and that does not need any external flame model. In fact, we consider the conservation equation for a reactive flow with finite rate chemistry with conservation of mass, of momentum, of energy, and species transport. This with a reaction rate given by this Arrhenius term for the finite rate chemistry. This one is recasted into a compact form of nonlinear equations with a state vector Q comprising the state variables velocity, pressure, temperature, and species mass fraction. This set of equations is linearized around a base state, Q bar, which is solution to the steady state equation. And we get the evolution equations from the linearized equation for Q prime, which is the fluctuation. Those are the linearized reactive flow equations that stem from the linearization of the nonlinear reactive flow equation without further assumption. Since the flame dynamics is intrinsically embedded in the linearized reactive flow equation, we can use this framework to compute the shape sensitivity delta lambda, accounting for the change in the flame dynamics. But there is another bottleneck. The linearized reactive flow equations are not as simple as the Helmholtz equation. This is a set of 4 or 5 advection diffusion reaction equations with non-trivial boundary conditions compared to the scalar parabolic equation for the Helmholtz equation. And these linearized reactive flow equations are tedious to put in the Hadamard form. This is not impossible, but it is enough motivation for us to propose an original alternative to circumvent this Hadamard form for the linearized reactive flow equation. And the main idea here is to see the shape modification as a base flow modification. And therefore, the shape sensitivity becomes a sensitivity to base flow modification. This is a very good starting point because we know how to compute base flow sensitivities from adjoint fields. So I will walk you through this. We start from the original eigenvalue problem for the direct and adjoint eigenvectors. And then we assume that the base flow is slightly perturbed by a modification delta Q bar here, resulting from a small shape modification. This changes the evolution operator for fluctuations by a small delta L, which is very small compared to the original operator. We can write the resulting perturbed eigenvalue problem with delta lambda here and delta Q being the drift of the eigenvalue and the change in the eigenvectors following the operator perturbation. I will now just reorganize the terms, and we see that the first term is simply the original unperturbed eigenvalue problem that we have on the first row. So it cancels out. The last term is infinitesimally small compared to the other terms, so of second order, and we can neglect it to have a linear approximation. We now want this delta lambda as a function of delta L here, but this delta Q term here is still unknown, so we need to get rid of the associated term. And this is where the adjoint magic happens. We multiply on the left by the adjoint eigenvector, and we see appearing here the adjoint eigenvalue problem that we have on the first row. And this term will cancel out. So we have now an expression for the drift of the eigenvalue for a small modification delta L of the base flow. But how to get this delta L? Well, it is the difference between the linear operator of the unperturbed and perturbed base flow. And the shape derivative is obtained by computing the ratio delta lambda by theta, the amplitude of the mesh modification, for small theta. Now how to compute it in practice. And this is where we propose a trick. We mesh the slightly modified geometry by simply shifting the nodes of the original mesh. On this figure, the white nodes are the mesh of the original geometry, and the orange nodes are the nodes of the slightly perturbed geometry by a given amplitude theta following the deformation vector v. Hence, we keep the connectivity of the mesh, which means that the element ij of the delta L matrix is simply the difference between the elements ij of the perturbed and unperturbed matrices. In the end, the delta L matrix is the difference of the stiffness matrices assembled on the original and modified mesh. So this is the trick that we propose to compute the perturbation matrix, and it is also the last piece of the methodological part. I will now present some verification to convince you that it does work, and we tested our method on two models. First, the Helmholtz equation for verification purpose. The eigenvalue problem is slightly more complicated, but the same derivation applies to get the eigenvalue shift delta lambda as the function of the base flow perturbation that is now reflected in a delta A matrix and a delta C matrix. We then test that on the linearized reactive flow equation, which is now a linear eigenvalue problem with a mass matrix, and similarly we can express the adjoint sensitivity of the eigenvalue with the perturbation of the stiffness matrix delta L and the mass matrix delta M. For both models, we use the proposed topology-preserving perturbation method to compute these delta A, delta C, delta M, and delta L matrices. We compare our results, again the one obtained from the Hadamard form on the Helmholtz equation, which are our reference results, and I will present only 3 test cases. The others are in the paper. The first one is the Reich tube, and we compute the sensitivity of the unstable thermoacoustic mode with respect to an extension of the duct delta L. So we computed the delta lambda, here the imaginary part and the real part, for several values of the domain extension delta L. And they all collapse on this asymptote as the mesh perturbation goes to 0. This means that the limit of this ratio here is effectively well defined, and the slope of the asymptote is the eigenvalue sensitivity with respect to the mesh extension. So we have a good quantitative match between the Hadamard form and the perturbation method. And if we follow those sensitivities from the perturbation method, we can nicely track how the eigenvalue evolves for longer and longer ducts. However, the method fails if we perturb the mesh in the heat source region. And this is a good reminder that we cannot handle optimization affecting the flame region with the Helmholtz solver, and that we should move on to the linearized reactive flow equation. Which is what we have done in the next case, in which we compare Helmholtz and linearized reactive flow approaches on a slit flame. This flame features an unstable thermoacoustic mode, and we compute again the sensitivity with respect to an extension of the combustion chamber downstream of the flame. On the left here, we can see the base flow, how it's computed for the linearized reactive flow equation. So the flame is resolved in space with the mesh here throughout the flame, and we see here the flow lines and the temperature fields for this non-parallel flow. The frequencies here for both models for this unstable thermoacoustic modes are slightly apart because the LRF accounts for the acoustic losses and non-zero mean flows, and also the flow topology, so the shear layers, the recirculation zones, and so on. The imaginary part of and real part of the delta lambda with respect to delta L converges to an asymptote here for small mesh extension delta L, and therefore the limit of the ratio defining the shape sensitivity, so this delta L over theta, is well defined. And we have a nice quantitative match between the sensitivities from the Helmholtz equation with Hadamard form as a reference with the proposed methods applies to the linearized reactive flow LRF with mesh perturbation, and this despite model differences. From a physical point of view, the sensitivity here tells us that the frequency is dropping and the growth rate is almost not affected, which is consistent with our understanding of thermoacoustic modes. We are now moving to the last case, which is a case that cannot be tackled with the Helmholtz equation, since we compute the sensitivity of the unstable mode on that slit flame with respect to an elongation of the slit. Hence, it changes the time delays of the thermoacoustic feedback loop, and so it changes the flame dynamics. This case now features an intrinsic thermoacoustic mode, so it's independent of the cavity mode here. And on that case, the modulus of the linear prediction here, the error in the linear prediction, is dropping when we decrease the size of the perturbation. This means that our method converges also in this case. The sensitivity here suggests a drop in frequency, which is consistent with the understanding of the thermoacoustic feedback loop in that case. So we have a longer slit, which means a longer convection times for the vortices from the leading edge of the slit to the trailing edge and therefore to the flame. So a longer time delay and therefore a lower frequency. So we here have an LRF model to compute the adjoint sensitivity, consistently accounting for the change in flame dynamics together with the change in the acoustics. So there is still an additional cost compared to the Hadamard method, because unlike the Helmholtz equation, the linearized reactive flow relies on a base flow that is solution to some equations. And that one needs to be recomputed to account for the change in the geometry. And this base flow recomputation here has a cost. However, this cost is rather low. In our approach, the base flow is computed through a Newton solver, and since the mesh perturbations are rather small, the unperturbed solution is initialized on the perturbed mesh and converges to the perturbed solution within a few iterations only. So in the end, we can say that we have saved some efforts in deriving tedious equations, but we have to invest slightly more computational time. The final question is about the size of the mesh perturbation. How large or how small can we choose them? The upper bound is set by the node displacement in the region of high gradient, so in the flame. This node displacement must be smaller than the smallest gradient length in this region to remain in the linear regime, so for this linear approximation on which we would like to hold. But actually we want the mesh perturbation to be as small as possible to shorten the computational time of the perturbed flow. And in that aim, the perturbation can be chosen as small as long as this ratio here, which is the one that we compute in the end, is not impeded by round-off errors. On this, I'd like to conclude. So we have presented a method to compute shape sensitivities from the adjoint fields, trading the Hadamard form for a mesh perturbation approach. In that sense, we strive to get the best of both worlds, adjoint methods and finite differences. This comes with a slightly increased computational cost. This method was applied to the linearized reactive flow equations, LRF, and in that way we consistently account for changes in the flame dynamics in the sensitivity. Therefore, the method can be applied to optimize any part of a burner. The shape sensitivities can be combined with any shape parameterization and standard gradient-based algorithm for shape optimization. And in a broader view, the perturbation method can be applied to any adjoint-based optimization problem constrained by a linear system. To finish, I would like to acknowledge my co-author and Ekrem Ekici from the University of Cambridge for making his code Helmholtz X available and providing support with it. Thank you, and I invite you to have a read at the paper with the link in the comment section.